doing like pre-submitted questions, gives me the time to prepare it a bit. So hopefully we can answer those questions proper and you are happy with the answer. So Henkel or Loctite, more specific. So Henkel is a multi-billion company, worldwide company with 60,000 employees, more than 20 billion revenue, and Henkel is playing a role in many different markets. So we have the adhesive side, which is more B2B, and then we got the consumer brand, which is more B2C. Maybe you've already heard of Persil, Schwarzkopf, and all that, or you only know Henkel from these brands. But a lot of people are always wondered, what does Henkel and Loctite do with 3D printing? Because we are Loctite. So Loctite 3D printing was founded in 2016 in Düsseldorf, where the headquarters is, so Düsseldorf, Germany. And from that, Henkel tried to do a lot of different things within the 3D printing. So we had our bonders and adhesives for 3D printing materials. We had our own printer and all that, but it didn't work out perfectly. So what we then thought, okay, let's focus on what we're really good at, and this is materials, adhesives, because the technology of DLP, LCD photopolymers is quite similar to UV reactive adhesives. So we already have a lot of experience in that field. So we said, okay, let's focus on that. Also, together with the acquiring of the company Molecule in 2019, we fully focused only on materials. We also have our own production site, which only produces materials for the 3D printing space. So we don't have to share capacities with other products, which is very unique within Henkel, because that's usually you always share those resources, and that allows us to being certified under the ISO 13485 and being very fast in producing and delivering our materials. We have in total 3 different sites. Heidelberg, where I'm located, then we got Dublin, and we got Concord in California. What are we offering? As said, we are materials only, and we cluster our materials in 3 different sections. We have the photoplastics, where we have the, let's say, the tough materials, like the ABS-like materials, or a PP-like materials. I don't really like those namings, but you get it. And the high temperature resistant materials, as well as chemical resistant materials. Then we have in the middle the photoelastic. So photoelastic is the elastomeric resins, because our resins are not elastomers, they're elastomeric-like, because the complete base of our materials is still acrylate, so the polymer acrylate, and just the additives and the different ingredients make the materials tending to one specialty to another. But we don't have like a real elastomeric, even though people saying about their materials that they're elastomerics. And then we have the last sector, which are the resins for healthcare. I will speak a little bit more about that later on, because healthcare can be very complex, and the approach in the market is very confusing, to be honest, because everyone is talking about biocompatibility, and by the end of the day, it's not working out and no one knows why. So I will talk about that a little bit more later on, but we for sure have materials for the healthcare sector for medical devices. That being said, I don't want to lose any time and then really jump into our materials. We are saying really that data is our currency. So our whole organization is built up in a way that we're fully focused on our materials and creating data, sustainable and real data. So on the website, we will make later on an excursus so I can show you a little bit more some tips and tricks where you can find some stuff on the website. But it's really all about our technical data sheets. That's our most valued document we have, and we try to have an approach to be able to which is give the customer as many data as possible. So compared to other conservative materials where you maybe have like 2 or 3 pages just with absolute data on mechanical properties and thermal properties, we really extended that to having more aging data, resistant data, and so on and so forth. So our technical data sheets are really our bread and butter. That being said, let's jump to the materials. And I don't want to talk about every material because we don't have the time for it. So we easily have now 13 to 50 different materials. I want to talk about just 4 materials. I picked those 4 for a specific reason because they are more or less a disruptor, and I want to talk about why they are. So the first one is the ESD material. So the ESD in 3D printing is not new. But what is new is the very high temperature resistancy of that material. So this material can easily withstand 200 C. It has an HET of 190, meaning that at 190 it starts to deflect under a certain load. It's a very stiff material, but also very low elongation at break. So that it's not a tough material. It's very rigid, very stiff, but high temperature resistancy. And in terms of ESD properties, it's in the middle because I'm not sure if we have people from the electronic space, but if you have customers in the electronic space and they're asking for an ESD safe material, that can literally mean everything within the range of the standard. So the standard is 10 to the 4 to 10 to the 11 ohm surface resistivity. So if you do the math, those numbers are it's quite a big gap. And that's also something we discovered or experienced when we were developing this material. So like, okay, we can be more, to the low side that is very much dissipative, or more to the isolator side. So what are we doing? So we asked a lot of customers what is their preferred range, and it turned out that it's like everyone got their specific desires. So we ended up being in the middle. Even though we display 10 to the 4 to 10 to the 11, this material is more in the middle when it comes to the ESD properties. So we try to cover the broad spectrum. And people are asking us, so what can I do with this material? And for sure, there's jigs and fixtures, there's tooling, there's soldering. But I picked out now a case study from Nokia because I think it's always the best thing to have something tangible to know what the material is capable of. So Nokia had an issue. They are having very expensive PCB boards. Those PCB boards, you don't just want to waste them, not just only because of the sustainability factor, but also because of the cost. So they want to repair their boards. And if they want to desolder a part, they need heat. But, it's very hard to concentrate it, have a heat beam on a specific area on a PCB board. You will always heat up the area around. So that's what's happening here. They're using an infraspectrum heat lamp, but they're also heating up everything around it. And this is an issue because you want to have the hot spot in the middle, your 250 C, but you also have high thermal stresses around. So you have uncontrolled heat distribution and you potentially damaging your parts on the board around it. So they thought about, okay, we need to have a shielding, a solution. And this is printed with 3380. So on the left-hand side, this is the final shielding. On the right side is just a rendered file to display that you have like inner channels with cooling and stuff, and they're using it directly on the PCB board with a small gap. They also protected it with another metal shield, but by the end of the day, they were able to decrease the temperatures around by more than 50-60 C. So all the other components on this PCB boards are safe now. So this is a solution they are now rolling out globally. It's really a big thing, and they needed to have a 3D printed part because you know the PCB boards aren't always looking the same. They always look different. So you always need to have a new geometry. So 3D printing just comes here handy. And yeah, I think that's a fantastic example, and we're very happy and thankful that we're able to present that because, you know, the coolest applications are always under confidentiality. So happy to present it today. That's the final PCB board with the shielding then in the end. And as you can see, the heat is only distributed to the processor here in that example. Then, next material I want to talk about is the 249. So our materials are, as said, acrylics, but they're also different to most of the other plastics in the world because there are no thermoplasts. Our materials are thermosets. So thermosets, by their nature, are very chemical resistant. And so we thought, okay, you know, our materials, they're good, or let's say compared to thermoplastics in general, they're good in chemical resistancy. But what about having a material that is really, really good in that sense? So we developed the 249. The 249 is a very stiff, very accurate material, easy to print. It has a good temperature resistancy. It's decent when it comes to toughness. I mean, 5% is not high. It breaks not fast, but you also can't throw it against the wall. But it has a really, really good chemical resistancy. So on our data sheets, we usually do a chemical aging where we expose our materials 1 day up to 7 days against a specific chemical. And this is an ongoing process. So the first round of chemical aging was done in the past years. And now we're doing the second round. So we already did an aging for against 7 chemicals, and now we're doing the second round. So this material here, you can also see the cover here for the gasoline tank. So this material is really good when it comes to chemical resistancy. Oh. Next material is in the medical space. So before I was starting to talk about the material itself, I want to cover a little bit about the medical sector as a whole, because I don't want to do or talk too much about it, but I just want to raise the awareness that medical healthcare is a very complex section. So people are always talking about biocompatibility. They're moving around, say, yeah, is your material biocompatible? Oh yeah, cool, then I take it and I use it for whatever healthcare application. And that's not right, because you can imagine that you need different testing if you use, for example, a hand brace for your arm, or if you want to put a part in your body. So one is definitely a higher risk than the other. So you really have to look what kind of certifications a material has, and what kind of medical classes to follow the European norm here the material can cover. And this material now, the MET 9851, that's our answer for medical class 1 and 2. So if you're asking what is medical class 1 and 2, it's everything at the body. Not in the body, maximum in your mouth. So dental is covered under a substandard of the class 2, but med class 1 is like orthotics, prosthetics, stuff like that. Medical class 2 is eyewear, not eyewear, hearing aids and dental, for example, and you're able to cover that with that material. But if you want to go higher, where very strong and strict extraction-based testing is needed, it's too much for this material. And that's not only for this material, it's also for most of the materials at the market. So being capable, or material being capable to pass all the testing, for example, of an FDA, of hospitals and all that is very rough. And just because you're reading biocompatibility doesn't mean that those materials can automatically pass the requirements. So the material, it's a very all-rounding material. It's super easy to print. It's very tough. It has good elongation. The HGT is decent with about 68, so it's not super soft at higher temperatures. Neither it's super resistant, but it's a very good all-rounding material. So you can really use it for most of the general purpose applications. But because I said that some materials can do higher grading, we invented the 3394. So this material is for hospitals. It is for surgical tooling. It is for applications in contact with tissue or bones. And we call it the sterilizable resin because theoretically you can sterilize everything, but the question is how the parts are looking afterwards. So this material was specifically developed for sterilization. It can easily withstand 25 cycles of steam sterilization without deforming or losing property. But the most important thing here is the biocompatibility standards we have on this material. It's not only the 5, 10, and 23, like the standard skin-based testings, but also acute toxicity and the USP class 6. So the USP class 6 is in its own ranking. So USP is something like the MDR or FDA. 6 is the highest level, and it's for a lot of applications required to have USP ranking. So the USP 6 is the highest. And here we have tested tissue and bone contact, for example. So if you have clean room applications, if you have hospital devices and all that, you can really use this material. Here on the right side is something I'm always astounded by this picture, because DLP as such, and this material particular, is the only material we have seen so far where you're able to print a block with fluid channels, where you also have the certification to be able to flow medical grade fluids through the system. So here on the right side, you can really build one block. Those channels are 1.5 millimeter thick, and everything is medical proofed. And that's actually a part we copied from one of our customers using that as a real application. That's really cool. All right, next point on the agenda is our Q&A and pre-submitted questions, because we are, it's not like a super huge webinar where I just want to go, those are my slides and then we're gone. We also want to target your specific questions. Sorry already, because I just got one monitor, so I need to stop sharing after your pre-submitted questions to be able to see the chat. But first, let's talk about your questions. So the first question I got was, what are the stress strain plots of your elastomeric materials and where can they be found? So here's the thing. If you need any data, which you see on our technical data sheets. Maybe you've recognized in the footnote very tiny in the bottom some F or R numbers. That's just for our internal codes, and with those internal codes we can go into our internal data management software and extract the testing. So this is a typical elastomeric plot here. It's very linear in the beginning, moving up like that, and just going a little bit more steep by the end before it snaps. So this here represents actually all of our elastomeric resins. So you never have a yield. You always will have this more or less linear curve and then the snap. But coming back to the data, so someone asked us here, that's also why I picked it as the first question, for a plot, for a graph, for the actual data, how it's being tested, and you can have it if you want it. You just need to ask us. We can extract it. We have all the legacy data we have done in the past 10 years on our in our software. So whenever you have questions to specific data or you need to have more insights, let us know. The second one, and it's a very common one, it's the 475 issue. The 475, for everyone who doesn't, where like the bell is not ringing, the 475 is an elastomeric material. We got it in white and black, and it has an issue. The issue is that when you print it and post-process it, it's sticky. And people, like, no one wants to have sticky parts, not because it's sticky and it's also because people think it's toxic, and that's not the case. So I can already give here can tell you that this is not the case. What is actually happening from a chemical perspective is when you're doing the post curing, what you want with the post curing, you put your light on, you activate the second reaction of your photoinitiators, and you want to have just only the components of your composition being reactive. But there's the oxygen. Oxygen is floating around everywhere, and the oxygen is very aggressive, and the oxygen wants to have a place at the chain of this material. And this is the reason why it's sticky. It's the oxygen. So the task here, the mission is keep the oxygen away. And how are we doing that? So there is the way of using water. Put the parts in a water bath, put it under your Dimex, your Uvalock, whatever unit was strong enough to cure the material, and it should be less sticky, depending if you're curing the black or the white. The black is already tag-free or sticky-free, but the white is really, personally, I have to say, like, I also don't like to work with this material. It's a cool material in the end if it's fully produced, but it's really hard to process. So the white needs a little bit more in process-wise. So for the white, what we're doing is we're using either like a mode release, like a free code or something. So we dip it in a mold release. With that, we're ensuring to create kind of an inerting barrier around about the part, and then we post curing it in water. So then it's completely tag free. Or you just have a tacky and you just use a silicone spray. It's that simple. I know that many customers they're not allowed to use a silicone spray because you're losing, like, you know, the ability to bond it to something else, and also other negatives can occur. But if you are, like, I mean, a lot of people using silicone spray in many different applications or situations, buy just a household silicone spray from, I don't know, WD-40, whatever, spray it, wait a couple of minutes till it's dry, and it's tag free. If that's solving your problem, go for that solution. If you're not allowed to do it, you have to go with one of the others shown here above. Then Third question. Could you suggest a resin that can withstand petroleum products, so fuel and stuff? We are currently doing the second round of chemical aging, as said, and the second round includes 7 chemicals from the automotive section, like braking fluid, gasoline, all that. And it's still not published. It will be published later this year, so we're currently consolidating everything. But what I can say that the 249 is still here the best candidate. It has, as said, the highest chemical resistancy, and it should be able to, like, I can't say it for sure because I don't know how long you want to expose it to and what are the other conditions, but that's definitely your best candidate for these kind of chemicals. And then lastly, before I'm going to the web page, I combined 2 questions because they're more or less going in the same direction. So the first question was how to choose the most suitable material for your application. Good question. And is there a library with all the technical data where by entering a certain known property, one can receive a recommendation for a suitable resin? I have here the screenshot, but I will now open the browser and go to the web page because we have, I think, 2 solutions which will help you going at least in the right direction. So let me just very briefly going into my browser to the web page. So it's the loctiteam.com, and under here we got product and resins, production resins. And under production resins, if you're scrolling down, there are 2 links. There is not sure where to start, find my material, and there is the material brochure. So the material brochure is something I use very frequent because a lot of numbers, a lot of materials, hard to keep the track of everything. So in this brochure, in this digital brochure, there are some tables with, you know, the most important properties, just the standard one, the most standard one, which are like the HET, so your heat deflection temperature, your elongation and break, Young's modulus, so your mechanical properties, your shore, and your impact resistivity. And here you have all the numbers. You can look it down, so you don't have to one by one click on each technical data sheet, scroll down, find the right property, and then compare it to your reference or whatever you're looking for. This brochure I can really recommend, and it also have like a very short version of each of those materials. So this is what I use usually. But if you are more the visual guy, we also have the product selector. So remember, here find my material. You will get to the product selector, and here on the right side you can look for high impact, high temperature, and elastomeric. If you click on one of these, you will get those bubble charts, and if you hover over those bubbles, you will see that under behind each bubble is material with some key properties. So here we got on X the heat deflection temperature, and on Y here the notched impact, and then you can see, okay, the 405, the 405 clear, the gray, you got here the 3843 white, clear, and black. So if you're clicking, you know, through all these different sections, you will always get a different bubble diagram with our materials, and you have a feeling how good or bad they are compared to each other. All right, that's it for the presentation content. I would now open up the Q&A.
Hendric, we have 2 questions in the chat.
Yes. Okay. So
The Hebrew one
I'm
is
interested
mine,
in food contact material, or already got a like. Yeah. Okay. I have to be very careful what I'm saying now, because of confidentiality reasons. The easiest answer here is stay tuned, because we getting food approval requests, I don't know, for more than 5 or 6 years. So we have looked into that for quite a long time, and I can't say more, but there will be something. There will be something, because out of now, also don't get distracted from certification stamps and documents. We have seen a lot of FDA stamps on technical data sheets from other manufacturers, and we thought, okay, that's very interesting that these guys having food approved materials, but they don't. So what that is, to not confuse you, is an FDA filing. So you can go to the FDA and you can register your material, and then you get the stamp, but it doesn't mean that it's food approved. It just means that your material is registered at FDA. So yeah, there will be something. Majid, okay, you were asking which materials can be flexible and abrasion resistant sandblasting at the same time. Oh, okay, that's an interesting one, because maybe you can specify it. So sandblasting, what kind of filling are you using? Are you using some wood, some plastic, or little stones? So with sandblasting also with the pressure, because sandblasting, the intention of sandblasting is to abrase the surface. So having something that is resistant against it, and it's elastomeric even, is very tough. My best bet would be the IND 402, just because it's the highest in shore, so the surface is pretty smooth. So it could resist. It will change the visuals for sure, but maybe it can resist. Yeah, but it's tough. It's tough to say. We would need to have that tested, to be honest.
Majid, does it answer your question?
Yeah, thank you.
Yeah, so if you that's just a general take I want to make here in this group, because we are partnering with Mafeel, and we also offer that to Mafeel all the time. So if you having very specific technical questions, and not you, neither Mafeel knows the answer, maybe we don't know it either, but you can always reach out to us. So if you directly want to contact us, you can always go via webpage or via Mafeel. So we always try to do our best. Maybe we have done something with different customers, and we can share it. So if you're curious into something specific, and you don't find the answer on our webpage, neither on ChatGPT, you can always ask us. Any other questions?
I will try to activate the audio. If someone someone has a question, feel free to ask, guys. The microphone is loud for everybody right now. So if someone wants to say something or to ask,
I have a
that's the
question.
time.
Hello,
Please.
my name is Alon.
Hey.
I'm asking about a kind of a varnish that you can put on afterwards, post-processing, on the 3D printed parts and get smoother surfaces.
Okay,
Do you
so
have
you're
some
looking
kind of
for a coating.
coating, some kind of coating?
Some kind of coating. Okay. Do you want to have a gloss coating or a smooth? So should it look more matte or more glossy?
No, more glossy.
More glossy.
Yeah, and if it can make the part more transparent, maybe.
Mm-hmm.
Not for the transparency, I need it for the surface finish. I want a very, very smooth surface finish.
Okay, yeah. I'm just trying to find, because we have a very a very good example. We did that at this time with carbon. So when we started the cooperation with Carbon 3D, we developed the 405 at that time, and the 405 clear it's good, it's decent at transparency, but it's not clear, it's not fully clear. So we were looking into specifically what you're looking for, a coating that increased the transparency, because the material itself is transparent, but it's getting fairy or smoky again when you clean it with IPA. So the only thing you have to do, the only thing, is use a coating or polishing it. So you can use a tumbler, you can polish it actually to full transparency again. But if you want to do a coating, I would always suggest a polyurethane clear coat, because those are very cheap. You can dip them, so you can, for example, use a pot or whatever. You can just dip in the pot, you can let it hang, let it getting dry, and then it's completely transparent. The only issue I'm always having with this kind of workaround is that you need to scale the parts down to the that you're by the end of the day still having the right tolerances, because for sure
What
if you
is the
add,
thickness added? Do you know?
it depends on the coating. Also, if you, for example, you can, if you want to use it on a flexible material, you need a flexible coating.
No,
And
not
flexible,
flexible.
not flexible. Okay, then it can be very thin, like 0.1 or something. So the scaling needs
Does
to just
Loctite have a material zug of clear coat?
I think we
Good
do.
question.
I think we do. We have like coatings and adhesives. I'm in Heidelberg. Our site is dedicated to adhesives for the automotive industry, and we on our site producing more than 1,500 different products. So it's hard to keep track of all of them. I'm pretty sure we have, but I also can't say that we're the cheapest. We're never the cheapest. Maybe we have the best quality, but we're never the cheapest. And if it's just increasing transparency, you can go with everything you want. So if you are just looking in the internet for a PU-based clear coat, you will already get something for, I don't know, 20 bucks. So for example, Silka, one of our competitor, they have a lot of these PU clear coatings.
Silica?
Yeah, Silka.
Okay, we will search. Thank you.
Yeah, no worries. If you have issues, contact me. We have done it in the past. I'm pretty sure that I can dig in our documents and find what we have used.
We have a few questions in chat.
Okay.
From Yoni, is there a type of curing machine effect on the curing duration?
Yes, absolutely. So you can think of the material as being, so if you are doing the reaction, it's like okay, simplistic said, but it's like baking a cake. So if you're asking if, like, I put the cake now in the oven for 10 minutes. On the manual it says 50 and you're just doing 10 at 180 C. Is it enough? It's not. So it is very, very important to have the right curing duration and the right curing machine. We are doing workflow validation. We're trying to cover most of the units in the market, but these days are also like hundreds of post-curing machines in the market, so we can't cover them all. But we try to do as much as we can. And we always do a workflow validation where we pair a printer, a post-curing machine, and then we're checking the mechanical properties in the end. And if that's the case, everything is fine, we put it on the web page. You always have to look for the intensity and the wavelength of those post-curing machines. It's not very trivial. So if you're just buying a random machine and you hope like, okay, here is a post-curing machine for hundreds of bucks, and I'm just buying it, and you know, on the paper it's the same as everything else, but the result is bad. It's just because it's not so simple as people describe it. So if you're looking for the right machine for post-curing, you should better reach out to Mefil or us. Are your materials also suitable for laser printers, such as DLP printers? No. No. Because we are like DLP LCD is the wavelength of 385 to 405. Lasers are usually at 365, so that's the first difference. The second difference is the intensity. Our materials, that's also why SLS materials are most of the time very brittle, because our materials need time to build up the chain and to have those mechanical properties. So they're not suitable for laser printers. The only laser printer that works a bit is the Formlabs, because it's such a low intensity printer. Then, okay, the next one is going to you, Ronan, per case contact. I think I already forwarded you the contact for Loctite. Then the next one is 3D printing resin with similar properties to Ultem. High heat and stress like the Ultem 98.5 or 1010. Okay, I need a very briefly check. Are those materials fiber reinforced? Because that's something we can't do. So we're trying to get the materials for sure. Like everyone wants to have a temperature resistant material, high elongation, food approved, low water absorption, you know, everything. We try to get at least to a level where the materials are not super brittle, but still having a decent heat resistancy. But we will never be able to compete with fiber reinforced materials. So the 98.5, I'm not sure what it is, but we can look it up. Like if it's a standard material, standard thermoplastic, maybe we have an alternative, but I'm not fully sure.
I will check it with Ron later.
It's not fiber reinforced. It's UL 94 V0, and it's a high temp, and it's it has a standard for the airplane industry.
I see. Yeah, I see. Okay. We have a material which is UL V0 certified, but that material is very brittle. It's super high temperature resistancy, over 300 C. It has all the Airbus standards, and it is for aerospace, but it has a elongation and break of 2%. We are looking into for something which is a little bit tougher, but that's something for the future. So if you don't need elongation or very high stresses, then the material is good. But if you need high stresses and some, you know, if you have some mechanics that approach the part, then the material is not the best. The material is called 3955. If you're interested in, you can check it out on the webpage. I will just put it here in the chat, so you got the number. From working with other known brands of high quality SLA resin, it's almost always came out to be more beneficial to cure inside of water, especially clear parts. That's an interesting take. I've never heard that before, but I'm also not too much into SLA. Cure them in water. So my gut feeling is telling me curing in water helps to absorb the heat. So, you know, if you are putting a part in a post-processing station, you turn on the lights. With the light energy comes also heat energy. So that it is very likely that your part can deform. But the water takes out the heat. So that's why I think that people think that that could be good to get out the heat and reduce the deflection of a part. Curing wise, so just from a chemical perspective, it's not helping at all, because it's either the other way around. Because if you think about the light traveling, it needs to go through the air. If there is water, that's another barrier the light needs to go through. So if you have a certain intensity and you have to go through water, the water will absorb some energy from the light. So in terms of reactivity, I would say the water is blocking the reaction a bit, but from when it comes to accuracy, I think it helps. But that shouldn't be the issue for most of our products. Only if we are talking about high temperature resistant products, which you may have to cure very long in the oven, stuff like that. There it can help. Yeah, I agree. But not for all the Loctite resins. For some, like the 475. But there, it's for another purpose.
I think we have one
What will
question
happen? Sorry. There's just one. You're welcome. What will happen in the case of overcure time? That's a good question. So if you are overcuring, you can think of it as a graph. So if you're having total energy on the y, and you have the duration on x, okay? And you're curing, and here is the threshold. If you're here, your curing is done. But if you're going over, there are two possibilities. If your post-curing device is strong enough to break the chains, then you will age the parts and you will lose properties. So, for example, you're using a Dimex, a very strong post-curing unit, and you overcure it, or you overcure already in the printer. For example, you need to have 5 seconds exposure time and you're using 10. The properties will most of the time very, very brittle, because once you exceed the needed energy of a material or of the reaction, you start the aging process. And depending on your intensity, you will just reduce the total lifetime of your product. So always be sure that you are within the given ranges of curing, because otherwise you have the potential that your part or your application can fail like earlier than you want. But sometimes also nothing is happening. We have also experienced if you're using, for example, very low intensity curing units. For example, taking the Aligu one. It's a very cheap unit. It's a good unit, don't get me wrong, but the machine is very low in intensity and power, and it takes very, very, very long to make the part breaking or failing, because the intensity of the machine is just not high enough to break the chains of the polymers. But for the rest of the machines, you should always be very, very careful and always follow the work instructions.
I don't think we have any questions. If anyone have any additional questions, so please jump in. And from my perspective, also, guys, if you have any ideas for future webinars, future discussions that we can bring up, also arrange also with Hendric, we'll be happy to arrange it.
Yeah. Yeah, absolutely. Just reach out via webpage, via Ronan or Alex. Always happy to help. And I can already say I'm very thankful to that we have done this webinar, because I think that's now in the past 3 years the 15th or the 20th webinar I'm doing, and like you are the most interactive one. So we had even like crowds of 60, 70 people, and you maybe get 2 or 3 questions max. And having already the pre-submitted questions plus all the questions here in the chat is fantastic. Very, very happy to see. That's really cool.
I think we are done. Hendric, everybody, thank you so much. Thank you for joining to the webinar, and
Yeah.
see
Thank you
you
very
again.
much.
Thank you guys. Appreciate your time.
A great day.
Yeah. Have a good day. Bye bye.
Thank you. Bye bye. Thanks.
Bye.